My name is Jordan Simpson. I'm going to demonstrate a little bit of a project I've been working for our MAE 535 class. I initially started working on ultracapacitors as my topic, which are kind of hard to come by, and they're really expensive, not necessarily available at your local Radio Shack. So just kind of go over some of the concepts of capacitance in general. What I've built here is actually a capacitor. It's 2 layers of aluminum foil separated by wax paper. So if you recall through class, we were able to determine that the capacitance is related to the surface area and the distance of separation between the 2 plates. This is just a parallel plate capacitor. So that distance is minimized to the limit of the wax paper. So capacitance equals area over distance times the dielectric constant, in this case of wax paper, which is around 2 to 3 compared to air, which is 1. So we're a little bit better than we could be with just air itself, but not too much, factor of 2, maybe 3. So what I have here is a DC power supply at 30 volts. It's regulated to 200 milliamps, so it's going to limit the amount of charge we can actually store in our capacitor. But we'll watch, once I plug it in, the flute meter should rise up to some value of capacitance, which turns out to be right around ½ microfarad, which is not incredibly large, but also recall that a farad is a huge amount of charge. It's a huge value for the capacitance. So it's not incredibly large, but at the same time it should be enough to generate a spark, which this is never the proper way to discharge a capacitor, and certainly an ultracapacitor, which is around, wow, let's see, at least 100,000 times greater than this. We're talking 1 farad all the way up to 10, 20, 100, 1,000 farads. So that could be really dangerous. But in our case, it's not too bad. So I'll disconnect our power supply here. Well, also look real quick. We'll verify that there's a potential, voltage potential between the 2 ends. So it's about 30 volts DC, which is what we really expect. So we'll just short it out here. Disconnect the one end. Should get a spark here, which we do. Pretty uneventful, but that did short it out. So now, as you can tell, we're down to about 1 volt there, almost 2 volts. So we learned also that the advantage of capacitors are rapid charge rates compared with batteries. Batteries, you know, take sometimes hours to fully charge, whereas a capacitor can take, you know, nanoseconds for smaller values, up to, you know, maybe a couple seconds, depending on what kind of circuitry you have. So what I have here is just a 6-volt power supply. It's unregulated. It's going to pump out its max amps that it can. We've got a small resistor there, which should draw it down a little bit, and the LED in line with it, which will tell us once we've reached full charge. So when I connect this lead, the green light should power up until we reach 0 current. So as I connect it, you watch it quickly dim. So here's 3, maybe 4 seconds. I've had it, and this guy's fully charged. This is 4,700 microfarads. That's the largest one available at Radio Shack that I can get. So we're still a far cry from what an ultracapacitor can do. And now what I have here is a simple DC motor. So I have a power supply here that I'll connect to it. We remember, you can think about Biot-Savart's law, which spoke about the force generated in a coil based on magnetic field intensity. So I have the magnet on the bottom, which is generating my magnetic field. I have a current flowing through the coil. As we can increase N, which is the number of turns, that can increase the force. And we can ramp up the current, which can increase the force. So the thought here would be, I'm limited to what I can generate via this power supply, this simple DC power supply. But I can blast in a burst of current via my capacitor and kind of increase the speed of my little motor here. So we'll go ahead and give it a quick test run here. So we can get it to a pretty good speed. You notice I have a magnet on top of it here, which is increasing the value of my magnetic field. So we know that force equals IL cross B. So increasing B, or increasing current, or increasing the path, which is the number of turns, can get this thing spinning faster, increase that force. So that's what I've done here. Now if I blast it with this capacitor, we would hope that it would, you see it continues to spin slightly, but not by much. So such a small value of capacitance really can't generate much current, especially not enough to replace the battery power supply. And one thing I wanted to mention also, still the right-hand rule. So as current flows through, we have our magnetic field is in this direction. Our current, follow the thumb, magnetic field is downward, and that tells us that the force is coming outwards at me, which creates that spin, that proper rotation that we would expect. So the trick to making this work is actually half on the tips of the coil. Only half of the insulation is removed around the diameter of the wire. So as it lays vertical, there's no current flowing through it. But once it reaches its flat point, there's contact between the uninsulated portion and the supports here, which allows that current to flow, gives us that force, and gives us that rotation. So it's like an off-on, off-on, off-on. And another option to increase that speed, we said, was increasing I. So if I would swap my leads to opposite sides, that would give me additional current on what initially was the off portion. So if I add these two to the top, for example, that would increase my rotational speed. However, by experimentation, I was able to see that the friction overwhelms the system, and so it doesn't really generate what we would expect it to do. And I think that's about it. I appreciate you guys viewing it. Thanks a lot.